So we were in this section of chapter 5 where we were talking about the Prelog rules or CIP rules, or you call them the RNS rules, right? They're where we assign the configuration of molecules. We assign the configuration of molecules, the chiral configuration. Like, is it R? Is it S? And that's what we've been up to. We showed a couple examples of this. I'm not going to review everything, but this is just one example of this molecule where we assign the priorities of each of the substituents on the carbon. That's the chiral carbon, or you could say chiral center or something like that. And remember that atomic number wins, so chlorine wins, and then hydrogen loses. And then between these two things, this thing has 3 carbons on it, this thing has 1 carbon on it, right? And so that's how we assign B and C. I usually assign A and D first, and then I assign B and C. And once you got them, there's like 3 different ways we learned to assign the configuration. And in this case, if D is going away, you can do the counterclockwise as S, right? A, B, C. Counterclockwise is S. If it was clockwise, it would be R. Remember, we also have the thumb method. I'm not going to review it this second, but it's, look at last lecture. And we also have that thing called the stick figure method. And that's usually what I use if the hydrogen or D substituent is going into the plane of the paper. And sometimes, sometimes that's the easiest way. Thumb method will always work, but that, I think I might be a little quicker if I just use the stick figure method. So that's all reviewed in the last lecture. We also learned last time that, what do you do if you have a molecule like this with 2 chiral centers, the bromine and the tert-butyl, and it's not much more difficult, but this is it's just a step further. First thing I did is drew the hydrogens in. I think the hydrogens always help, right? And then you can, and what I did is reviewing from last lecture, I first assigned this with its A, B, C, and D's, and I got R out when I did that. But then I erased that all. I erased the A, B, C, and D because it's going to get in the way of the other one, right? So we did the careful determination that it's R on number 1, and then we determined that carbon 3 was R also. And the way we knew that, well, anyway, yeah, this counterclockwise, ABC. Counterclockwise you'd think is S, but remember the hydrogen's coming towards us, so it would be opposite. Or you can use the thumb method. Anyway, after doing all that, we determined it was 1R, 3R. How did we determine the numbering system? 1, 3, like 1, 2, 3 instead of 1, 2, 3. That was due to the alphabetical relationship of Br versus tert-butyl. Bromine is lower alphabetical than tert-butyl. Okay? Alright, so the end result was 1R, 3R, 1 bromo, 3 tert-butyl cyclohexane. Alright? The other thing we did last time was like, how would you go from a name to a structure? How would you go from a name to a structure? So I gave you this 1S, 2S, 1 bromo, 2 chloro, cycloheptane as an example. And the trick, and this is what we did at the very end, was you start by just drawing something, 1 bromo, 2 chlorocycloheptane, but without actually really caring about stereochemistry, and then you figure out were you right or not. And in this case, like we drew something, and then I checked 1, I checked 2, figured out that 1 was wrong, 2 was right, so then I just flipped 1 and it became dash dash dash. Okay, so that was the other kind of trick we learned last time. Okay, so moving forward, we're still on number 4, nomenclature, and it's the CIP method, Prelog method for RNS configuration of chiral molecules. All right. Okay, so let's see. Here's just another simple example, but you know, where we have to figure out the priorities. Sometimes it's a little more work to figure out the priorities. So ch3. Okay, and so where's the chiral center? And sometimes people still have confusion with that. Of course, that's not a chiral center because that would be you have a carbon with the two methyls are identical, and then you have the hydrogen. You need 4 unique substituents. So that's a chiral center over here. And yeah, so maybe draw the H in. All right, that helps. And now I do my priorities. So who's A? Well, who's D? D's easy. H is the D, right? We're often used to seeing, you know, the dash or wedge thing as being A, right? That seems to be the theme. But this CH3 is not A, right? Because the rule is we walk away until the first point of difference in this case. Okay, so H loses. Now who's A? Well, okay, you know, is it this thing with 1 carbon on it? Is it this thing with 0 carbons on it? Or is it this thing with 2 carbons on it? It's going to be this thing with 2 carbons on it. So that's A, right? All right, so then we have methyl versus ethyl. Who wins? The ethyl is going to win. And then we have this. So that looks like R or S. With D going away, it's really easy. It looks R. Okay, so it's to build a name, let's build the full name, and we'll first ignore the fact that it's R. Okay, so do I number left to right or right to left? Do I go 1, 2, 3, 4, 5, or do I go 1, 2, 3, 4, 5? The answer is I go in the direction of the first substituent. That was chapter 2. So it looks like build a name right to left. So pentane. Okay. So it's pentane, and then it looks like on this pentane I have a, you know, that's carbon 1, 2, 3. It looks like 2, 3 dimethyl. 2, 3 dimethyl. Technically, there's no space there. That's not something I care about, but it usually would actually be one big word, whatever. Okay, so we made the name minus the stereochemistry. How do we add the stereochemistry? All we say is R. Okay. Do we have to say 2R? Or I mean 3R? Because the chirality is on 3. 1, 2, 3. The answer is no. We don't have to say 3R. Because what would the 3... The 3 is unnecessary. It's redundant because 3 is known to be the chiral center. Okay. In what cases do you need to specify the location of the chiral center? And the answer... was like from before. Remember before? Where we had like a molecule that had 2 chiral centers. So in this case we had to say like 1R, 3R or something like that, right? And also, you know, in this case I gave you the name, but yeah, 1S, 2S, those refer to the position of the chiral centers, okay? But here we don't have to do that because there's only 1 chiral center. And it's on carbon 3. Yep. Okay, let's do a scary one. In the spirit of Halloween. Okay, so let's say H3C. Okay. All right. So let's look at this scary one here. And first of all, notice I am doing something that I want you to recognize. Whenever I draw chiral centers, it'll be some kind of like a zigzag, or you know, like a angled piece. And then we have the wedge and the dash, kind of like that. It's always going to be like that, or it might be this. You know, A, B, C, D, whatever. It's always going to be kind of like a zigzag, and then you have the wedge and the dash kind of offset, or like this or something. But what will it never be? It's stuff like that is never going to happen, right? It's because that does not depict a tetrahedron at all. You need to be able to depict a tetrahedron. That's a clear tetrahedron. That's a clear tetrahedron. That's a clear tetrahedron. This is not a tetrahedron. So as drawn, this is completely meaningless. On the website, I have a bunch of examples of like poorly drawn and better drawn chiral centers. So you take a look at that. All right, so let's look at the scary example. So what do we do first for the scary example? Probably pick the priorities, right? All right, so there's the chiral center, and here's A. Probably the oxygen, right? It's an atomic number. Yeah. So that's A. Who is the D? Usually I do A and D, and then I figure out B and C. Well, there's no hydrogen, so you're used to seeing a hydrogen as the D, right? There's no hydrogen, but in this case, it's probably going to be the CH3, because this is a carbon with 1 carbon on it. This is a carbon with 3 carbons on it, extended outward, 3 carbons. This is a carbon with 0 carbons on it, right? So very clearly this will be D. Okay, and then now B and C. Well, probably the tert butyl is going to be B, because it's got 3 carbons on it. This has got 1 carbon on it. So we have B, and we have C. All right. All right, so how do we determine the RNS now? This is a case where the thumb method will probably work. It will absolutely work. But when the D is in the plane of the paper, I usually would recommend just drawing a little stick figure. And where should you draw the stick figure? It's always going to be on the side opposite of the D substituent. So there's the D on the left. We're going to draw the stick figure on the right, and we're going to have them look at that carbon. What do they see? What do they see? In terms of, relative to them, what do they see? It looks like straight up is the B, right? Okay, and what does the dashes mean here? The dashes mean it's going into the paper. Or from the stick figure's perspective, it is to their right. So A is to the right. And from the stick figure's perspective, this thing, the ethyl group, is where? It's to their left, because it's coming towards us. When we're looking at it, it's coming towards us. But from the stick figure's perspective, it's coming off to the left. So that looks like C. Okay, and now we just use our clockwise counterclockwise rule. And is it R or S? It's S. Okay. But the name of this is actually very complicated, and we're not going to do it, because this is ether. Ethers have weird names. We will learn about ether naming later when we do the ether chapter. That's actually a few chapters away for us. But for now, we can't really name it, but we can assign R and S to it, okay? Okay, so we're still on number 4. It's kind of a long section. CIP, right? Kahn, Ingold, Prelog rules. We're on to C now. We're moving a little forward. Double bonds. We haven't seen double bonds yet. So a double bond is equal to multiple single bonds. That's the easiest way to do this. Multiple single bonds. Okay. So let's see an example. Okay, this is a very simple example. Alright, so here's the A. Off the carbon, here's the A. Because we have a couple carbons, we have an H. A is Br, right? Here's the D. The H. Here's the B and C. So when I say double bonds are equal to multiple single bonds, I mean that this double bond is kind of like there's 2 carbons hanging off this carbon outward. There's like carbon and a carbon. In terms of the rules, it's the easiest way to do this. So this is going to be B, and this is going to be C. Okay. Now, the book goes into a little more depth. And I think it's a little confusing. So if you read the book, just realize they are probably over-confusing it a little bit. What I just showed you is totally acceptable, and this will get you to where you want to go. There's a little bit more to this. It's just not really critical for our treatment of this. Okay, so if you just consider double bonds equal to multiple single bonds, you are set. It works every time. Okay, so is this RS? It looks like it's D going away. It's really easy. It's A, B, C, A, B, C. Looks like it's clockwise or counterclockwise. Looks like it's counterclockwise, so it's S. Okay. Oh wait, did I screw up? No. I actually, yeah, that's S. That's S. In my notes it says R. I think my notes are wrong. Haha. Yeah, that looks counterclockwise. That's S. Okay. Okay, so my notes are wrong. That's an S molecule. Okay. All right. So another example of double bonds, which are equal to multiple single bonds. Let's draw a benzene. With a chlorine going back and a hydrogen coming towards us. Chlorine going back, hydrogen coming towards us, and we get the ethyl out there. Alright, so how do we assign the priorities, and then how do we... Oh yeah, one more thing. Back to this one. I called it S, right? This one was S. But the name of this is complicated because it has an alkene in it, and that's a whole different naming system. For alkenes. So that's actually several chapters away. So in a case where the name is complicated, you would never do the name, right? We'll do the name later. I think this would technically be called 3-bromopentene, 1-pentene, because it's 5 carbons, but that name is, you know, that's the alkene chapter later. Alright, so this guy, who's A? A is probably the chlorine. Who's D? Probably the hydrogen. And now it's a case of, you know, this carbon versus this carbon. Well, clearly this carbon has, it's connected to 2 other carbons, right? But in addition, the double bond makes it actually act as 3. It's like an extra bond. So it's like this carbon is really, in terms of the rules, it's connected to 3 carbons. 1, 2, 3, because the double bond counts as an extra one. So that's like a carbon bound to 3 carbons. I'm not counting the back carbon, the carbon in the back. Okay, and of course this carbon is connected to 1 outward carbon, right? So 3 outward carbons, 1 outward carbon. So clearly it's going to be B and C. And now you have to choose R and S. There's a couple ways to do it. One is that ABC seems to be going to the right, counterclockwise, right? And you might say, oh, it's S. But remember, since the H is coming towards us, it would be the opposite. It would actually make it the final answer R. Okay? Remember how we did that rule? Alternatively, I can use my thumb, and I'm just going to jump to my right hand, because I think it is R. Let's check if it's R. Point my thumb towards myself. Point my thumb towards myself, and then I wrap my fingers and I see, oh, A, B, C, A, B, C, A, B, C. Right hand R. So, yes, it's R. Okay. Let's try a harder example. I think this is menthol. I'm going to put a question mark. I think it might be menthol. All right. How many chiral centers does this guy have? It's got 3. 1, 2, and 3. There's 3 chiral centers. Let's figure out R and S on all of them. Okay. I'm going to start at the top. And yeah. So, what's my priorities? That's clearly the D. That's a good starting point, is the D. Alright. Now here's my A. Well, it ain't that, because that's a carbon with 0 carbons on it. And maybe it's either this or this, right? So it's this or this. And you just keep walking away till the first point of difference. Well, no difference yet, so you go further, and it's like, oh, well, that's the A. This is the A, right? A. Okay, there's our A. And then it's like, B and C. Who's B and C? Well, this has to be C because it's a carbon with nothing. So C. And this is B. All right. So then it's D's going away. This is really easily R. R. So point a little arrow and say that's R. Okay. Okay. Then I usually erase stuff. Once I figure it out, it really helps to erase, because otherwise you get confused. So have a really good pencil with a really good eraser when you're doing this stuff. Alright, so we figured out R for that one. What about the hydroxy one, the alcohol? Okay, so here's A, B, C, and D. Oxygen's A, that's easy. This is D. And now I have to walk away till the first point of difference, and I'm like, well, is it, who's B and C? Well, that's a carbon with 2 carbons on it. This is a carbon with 1 carbon on it, so I think this is going to be B. And this is going to be C. Alright? So it helps that our D's going away. It looks like I'm going clockwise, 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 clockwise. D's going away, clockwise, clockwise. It's R, right? Erase stuff. Okay, this is R. Now, what's that thing called at the bottom? It's an isopropyl group. We have an isopropyl group down there. Alright, so let's try the priorities. Who's D? D is going to be the hydrogen. Alright, D is the hydrogen, and then I'm like, okay, I need my A's, my B's, and my C's. Now this is an interesting question. Who's A? Okay, because this is a carbon with 1 carbon and an oxygen. This is a carbon with 2 carbons on it. Okay, who's going to win? With oxygen is always going to win here. Oxygen will always beat carbon. Okay, and so this is going to be A. That thing, this carbon is A. I could put the A a little closer to the carbon, whatever. Now, but just as a point that I'm just going to make, what if I had an extra carbon here? Because this brings up a situation where, like, you might say, oh, this is 3 carbons versus this is 1 carbon and 1 oxygen. Who wins in this situation? And the answer is still the oxygen wins. That oxygen will beat, if I have more, multiple carbons here, it still beats it. Now I'm going to erase that carbon because that's not really there. Okay. Alright, cool. So we have A. Now, of course, who's going to win? Who's B and C? Well, that's B and that's C, because this is just a carbon with 1 carbon. There's a carbon with 2 carbons. Alright, so now I have B, and this is C. Alright, so I see the H coming towards me. I'm just going to jump straight to the thumb method. I'm going to try my right hand first. And I see, my thumb's coming towards me. If I write right hand, ACB is not going to work. Right hand, if I go ACB, right hand ACB does not work. Okay, let's try my left hand now. Hydrogen's coming towards me, and I go ABC. ABC, left hand works. Okay, left hand works with the thumb method. What is it, R or S? It's S. Lastly, I'm just going to erase all my work. And that's okay, you know. On the quizzes, I'm just going to ask you, is it R or S? So you don't have to show your work for the quizzes on these kind of problems. Okay, let's redraw the parts that got erased. Methyl, methyl. Okay, so from the top down around, it goes R, R, S. And actually, let's be clear and move the S is to the carbon, right? It's not on the H, it's actually on the carbon, because the carbons are chiral. R, R, S. Okay, I just checked that this is menthol, but this is actually L-menthol. L-menthol. What does the L mean? What does L mean? L has nothing to do with R and S, right? L. L is the same as minus. What does minus mean? Minus means it rotates light to the left. Okay, so it's levorotatory. That's what the L means. Levorotatory. Rotatory. And it's just that optical property of optical rotation. Okay, but L doesn't. You know, you can't interpret L and be like, oh, well, L means RRS. No. RRS is a structural property. L and minus are an optical property. Okay, so I'm showing the website real quick, and I'm going to go down to, this is the public website with all the homework and reading assignments and stuff. Go down to chapter 5. And there's a section of kind of good practice problems on morphine and dextromethorphan, and these are good practice for the quiz. So determining R and S for kind of slightly more complicated molecules. Now that we're getting good at this, we'll expect slightly challenging problems. So we go to this link here. I will have a key for this, maybe Monday. So you can check your work, and you should. And it'll also, what I'll also do on the key is I'll carefully step through the assignments of each of the chiral centers. All right. But for now, let's try dextromethorphan out. Okay, so here it is, dextromethorphan. This is cough suppressant, Robitussin DM, Robitussin dextromethorphan. All right. So where's my chiral centers? Oh, there they are. 1, 2, and 3. All right. So let's just quickly try 1, 2, and 3. All right. So looking at 1, and when you're doing this, and I'd recommend print this out, or make a PDF, and you can add your little labels of A, B, C, and D. Who's D? Oh, the hydrogen's going to be D, right? D's going away. That's going to help us. All right. Who is going to be A? Well, off the carbon. A nitrogen. A carbon bound to 2 carbons. And there's a bridge, right? There's a little bridge there. So it's that's A. This is going to probably be, I imagine it's going to be B, because it's a carbon bound to 2 carbons. This is a carbon bound to 1 carbon, right? So that looks to me like A, B, C. And H is going away, right? H is going away. All right, A, B, C. And H is going away, and it's counterclockwise. Counterclockwise is R or S. That's S. So that's actually pretty easy, right? Number 1's easy. Let's try number 2. Alright, so now it looks like scary H is coming towards us, right? Thumb method might be a good option here. I think that's going to be D on carbon number 2. And now it's like, who's going to be A, B, and C? Well, I got this is a carbon with 3 carbons on it. Ah, but this is a carbon with a nitrogen on it, right? This is a carbon with a nitrogen and 1 other carbon. So who's going to win? The carbon with 1 nitrogen and a carbon, or a carbon with 3 carbons on it? Remember, the atomic number always wins. So nitrogen is a higher atomic number than carbon. So this is going to be A. Here's D. Here is A. Okay, so we got D and A. Now who's B and C? A carbon with 3 carbons on it, or a carbon with 1 carbon on it? Who's going to be B? This is going to be B. So looking at number 2, we have D, we have A, B, and C. So easy way to do this is with your thumb. What I'm going to do is I'm going to poke my thumb upward, or towards me, and I'm going to imagine going from A to B to C. I'm going to try my left hand. A, B, C. A, B, C. Keep your thumb pointing towards yourself. A, B, C. Left hand seems to work, right? Left hand seems to work. Yeah, it works. Try my right hand. It's going to go A, C, B. That does not work. So left hand works. Thumb works here. That's S. We determined this was S. We determined this is S. All right. What about carbon number 3? So 1 and 2 are S, right? All right. So what do we do? This one is a little tricky, and the method to do this carbon number 3 is the stick figure method. I will show that on the key, but I'll show it on the key how to do the stick figure method. But for now, I'm just going to use my thumb for it. All right. So carbon 3. All right, who is the A substituent? Who is the A substituent first? We have 4 carbons, right? Is it this carbon with the benzene? Or is it the CH2? Or is it this CH2? Or is it this CH with 2 carbons? Who's A? Carbon 3 is a little scary, but we'll get through it, all right? All right, so carbon 3, it's either a carbon with 2 things on it, a carbon with 1 thing on it, or a carbon with 1 thing on it, or the benzene. But remember, the double bond is the double bond itself is like two single bonds. So this is like 2 bonds, and this is a 3rd bond. All right. So this is actually a carbon with 3 things on it. Carbon with 3 things on it, a carbon with 2 things on it. So I think it's going to be A and B, right? So far we got A and B. A on top, B there, okay? Now here's C and D. Okay, A and B, right? A and B. C and D now, how are we going to do C and D? So that's scary because they're both CH2s, right? What do you do if you just have CH2s? You walk away till the first point of difference, right? Alright, so if I walk away till the first point of difference, okay, CH2, CH2. Okay, now I go to this one. This is a CH2 with a nitrogen on it. This is a CH2 with another CH2 on it. So this is going to win. This is going to become C, right? And this thing is going to become D, the carbon in the distance. All right. So to recap, we have A up top. This is A. We have B, A, B. This is C, and this is D. A, B, C, and D. And the D is in the plane of the paper. So how do you do that or the computer screen in this case? How do you do it if the D is in the plane of the page? You can either use the little person, stick figure method and just draw the stick figure back here and show what it looks like, or I can use my thumb. I'm going to try my thumb and point in the direction down to the right. I'm trying my left hand first. And if I imagine my fingers start up here, that's A, they wrap around down to B and come all the way around to C, A, B, C, A, B, C. It seems like my left hand's working. A, B, C, A, B, C. Left hand seems to work. If left hand works, is it R or S? Left hand works, it's S, right? It is S. And on the key, you'll see that clearly, and you can draw a little stick figure out here in the middle of the ring. Draw a little stick figure in the middle of the ring and say, what does that stick figure see? And you're going to see that it is A, B, C counterclockwise S. Okay, so we just determined it's S, S, and S. All right. So this is a great type of problem, and for practice, the other one is morphine. Okay? I'm not going to do this one for you. You can try this, and I'll give you some more suggestions like for preparation for the quiz. And yeah, see if you can do 1, 2, 3, 4, and 5. Some of them are easy. Some of them are tricky. I'll post a key later, and then you can see if you got them right. All right, so for now, try 1, 2, 3, 4, 5. What do you do with a double bond? Like the double bond is assumed to be 2 single bonds. And then for the most part, though, this is actually pretty straightforward. Carbon 3 is a little challenging. I think 3 is the most challenging. Everything else is actually pretty straightforward. Alright, so we're done with number 4. We're done with the Klein-Engel Prelog. Try those practice problems, try the morphine, try the dextromethorphan, make sure all that makes sense. Now we're on to number 5, which is Fischer projections. Fischer projections. This is a different way of depicting chirality. I'm going to say it's very brief. We're not going to spend a lot of time on this, and probably not quizzable, not on quiz. Exams and things like that. But we're just going to mention what it is because the book mentions it, and it's kind of useful to know about. It's a little bit of a historical nomenclature. So what the Fischer projection is a method for depicting tetrahedral carbon. That's a little, it's used in some situations, and particularly like for carbohydrates and sugars and things like that. Okay, so that's where we're going to see it. What is a simple example of a Fischer projection? So if I envision a carbon with, we'll say an ethyl on the right coming towards us, and a bromine coming towards us on the left, and a hydrogen going away from us on the top, and a methyl going away from us on the bottom. The Fischer projection of this is that we would just draw it like this. CH2, CH3, CH3, Br. So this is a Fischer projection for this, or you could say, like, if I have a Fischer projection and I draw it this way, what is the meaning of this Fischer projection? And the meaning is that, yeah, the horizontal things are kind of coming towards us, and the vertical things are going away from us. I always remember this as it's like a bow tie. So you have a little bow tie there on the carbon. Okay. Yeah. So a little bow tie. All right. The horizontal are coming towards us. The vertical are going away. Just a couple more examples of just, what we mean here. Aldehyde, OH, H. Okay, so that's a Fischer projection. What's the meaning of this Fischer projection? It would be the horizontal things come towards us. Vertical things go away. All right. This is a simple carbohydrate, sugar. Carbohydrates are things that contain carbon, oxygen, and hydrogen. Carbohydrate, and the hydrate kind of means like almost like you have multiple waters or whatever. Oh, I screwed up. It's not a carboxylic acid, it's an aldehyde. So there are aldehydes up top. Simple carbohydrate called diglyceraldehyde. Okay, so still probably not clear to you, like why would we even do this, but if you have a bunch of chiral centers, sometimes this is it's actually easier to draw the Fischer projection. So, for example, glucose, which you're probably familiar with as an energy source, glucose is drawn sometimes as a Fischer projection. With an aldehyde on top. First OH to the right, second OH to the left, OH, OH on the right, H, 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 okay? Something like that. So that's, you can see, you know, with multiple chiral centers, this is actually a pretty easy thing to draw. Drawing the chirality of glucose is a little bit of work. So yeah, you know, this isn't a huge focus in the course. You will see them from time to time, though. Just be familiar with what it means. I think figure 24.1, so that's like way down the road, has more examples of some Fischer projections that are stereoisomers of sugars, isomers. So there's lots of different sugars. Glucose is just one of them, and there's other ones, mannose and fructose and things like that. And ribose. Ribose is the basis for DNA and RNA, right? And yeah, so you can see some examples of more sugars as Fischer projections. Oh yeah, this OH I didn't draw the H for. I should, but I guess sometimes people just, when they're drawing sugars, they just skip the H's altogether. So they just focus on the OH's. So you'll see that from time to time too. So, because it just gets a little crowded when we're drawing all this different stuff. So sometimes you'll see it with the H's, sometimes you'll see it without the H's. Okay, just a weird Fischer projection thing. All right. Okay, that was number 5. Now we're on to number 6. 6 is molecules with multiple stereocenters. Molecules with multiple stereocenters. And we're going to introduce a concept that's kind of like enantiomers, but it's a different relationship, because remember, an enantiomer is a relationship that chiral molecules have. So this is another relationship, and these are called diastereomers. So some molecules will be enantiomers, and some molecules will be diastereomers. D-I-A-S-T-E-R-E-O-M-E-R-S, diastereomers. Sometimes I abbreviate that as DS, just like I abbreviate enantiomer as EN sometimes. Okay. Alright, so this is the Mark simplified version. The book goes into some detail that I think is a little unnecessary and a little confusing. So let's give the Mark simplified version of diastereomers. And let's show a simple example first. Okay, so let's draw a molecule, a chiral molecule. So this is a chiral molecule. How many chiral centers are there? There's 2 chiral centers, 1 and 2, right? And let's draw the enantiomer, EN. The EN, the enantiomer. Remember, there's multiple ways we can draw enantiomers. I am going to draw it this way, where I just keep the benzene in the same orientation. I think that's, you know, it's one of the ways you can draw enantiomers. I like it most of the time. And if I do that, what's the enantiomer look like? Well, if the BRs are going towards us, now the BRs are going away from us, right? Okay, and if I remember, there's that other way to draw an enantiomer, which is kind of like sort of focusing on the mirror image relationship, because these are mirror images. You can't necessarily see that they're mirror images here, but there's the other way we can draw these that shows them to be mirror images, maybe a little better, and that would look like that. So, of course, now you can see the mirror image relationship of this molecule to that molecule, and that's, you know, these are enantiomers. These are the same molecule, just drawn from different representations. So I can write a little equal. Those are the same. If I take this and flip it over, take it, flop it over, it's that, right? Take this, flop it over, it's that. So those are the same molecule. These are two different ways of showing this enantiomer, right? Okay, and they're enantiomers. And what's, I'm not going to do it for you, but let's figure out, well, I'm going to tell you the answer. I'm not going to step through it. But what's the R and S for these two guys? If you do it, it's R and R. I can do my thumb method real quick. BR, A, B, C, D's going away. Right hand goes in, R. Right. Yeah, left one's R, right hand R, R. Try the other one. Hydrogen's going in. A, B, C. Hydrogen's going in. That's right. That's clockwise. That's also R. So RR. Okay. What would these then be? If these are RR, these must be. If they're an enantiomer, it must be what? The opposite of R is S, and they are S. Okay. So if you do the R's and S's, you'll get S. You'll have to either use the thumb method or realize that the H is coming towards you now. So yeah, went from RR to SS. Now these are the same molecule. These are the same. So if this is SS and this is the same, this must be SS. Make sure you can get those. Okay, that's SS. That's have to be SS, right? Okay, so it went from RR. The enantiomer is SS. All right. So what happens now? If it apparently going from the enantiomer to, you know, this to the its enantiomer, it flipped both chiral centers. What would it be if I flipped only one? So if I had the benzene, I got my chain of 3 carbons. Let's keep the left one static, and rather than flip both of them, I'm just going to flip one. And that is what a diastereomer is, DS. DS, diastereomer, which is this word we introduced, diastereomer DS. I'll define it in a second. Okay, and what are the R's and S's now? The left one's still R, right? But the right one is S. Because I only flipped one, right? Is this molecule chiral? Totally chiral. If that's chiral, this is chiral. If, you know, these are chiral. Yeah, it's chiral. And if it's chiral, it must have an enantiomer. So what's its enantiomer look like? Its enantiomer, if this is RS, the enantiomer must be SR. And its enantiomer, of course, would have both chiral centers flipped. So now it's BR, BR. If this is RS, this must be SR. You can double check that. That's RS, this is SR. You can totally double check that. Okay. What's the relationship of these two? Because it looks like this is SS, and if we imagine now like going from here to here, flipping just the right side one from S to R, what's its relationship? So its relationship is also diastereomer. Okay. What about the top left molecule to the bottom right molecule. What's the relationship of those two molecules? RR to SR. So it's also going to be, if you're flipping not all chiral centers but like one, or anything but all of them. If you have two, if you flip one of them, you go from RR to SR. Well, that's a diastereomer. What if we go these two guys? What are those? What's the relationship of all those? Bottom left to top right, that's diastereomer. So I guess a point here is that how many mirror images can a molecule have? How many mirror images can a molecule have? The answer is always one. You can't have more than one mirror image, right? The mirror image of RR is SS. So in an enantiomer, when you consider enantiomers, there's only one enantiomer. It's a partner, right? But a molecule can have multiple diastereomers. So this molecule is a diastereomer to this molecule is a diastereomer to that. So there's multiple diastereomers, okay? All right, so let's define diastereomer. Now there's multiple definitions for diastereomer too. I'm going to give the Mark simplified definition, and there's maybe more correct definitions the chirality nerds would provide, but I'm going to give the simple Mark definition, which accounts for most of the diastereomers you're going to see in organic chemistry, are molecules with two or more chiral centers. With the same connectivity. That are not enantiomers. We should also say and are not the same molecule, and not same. Because if they're the same, they're not diastereomers. They're not enantiomers or they're not the same, right? So basically what that means, easy way to think about that is if you have multiple chiral centers, and we need multiple chiral centers to experience this. Single chiral center, you're not going to have diastereomers. With multiple chiral centers, if you form a stereoisomer that is, if you're flipping both or all of the chiral centers, you get an enantiomer. If you flip one, or anything that's not all of the chiral centers, you get a diastereomer. So this is a great example of it. Okay, so molecules with two or more chiral centers with the same connectivity that are not enantiomers and that are also not the same, because if you have two molecules that are the same, well, they're not diastereomers, right? All right. So we're still on number 6, diastereomers. Let's just show another example. Let's have bromo-chloro. 1 bromo, 2 chlorocyclohexane. 1 bromo, 2 chlorocyclohexane. And we have a H there and a H there. Okay. Alright, so we have bromo-chlorocyclohexane. And how many chiral centers? 2. So the possibility of having diastereomer is possible. It is a chiral molecule, so it must have an enantiomer. I'm going to draw this and keep the same orientation. To see the enantiomer, I think it's useful to show the same orientation. So bromine was coming towards us, now the bromine's going away. Chlorine is going away, now chlorine's coming towards us. Alright, so we have, that's a nice enantiomer, right? What's the R's and S's? I will just write in RR You can double check that. That's RR on the left. So if that's RR, this must be SS. You can double check that. Okay, it went from RR to SS. What's the mirror? You know, this doesn't easily depict the mirror image relationship, even though those are non-superimposable mirror images. So the other way to draw this, of course, will look more like a mirror image to this, and that would look like that. And now you can kind of see the mirror image relationship. You know, this and this are mirror images of each other. This and this are the same molecule. It's just a different way to show it. Okay. Alright, and if this is SS, this must be, if it's the same molecule, must be SS. How can you confirm that these are the same molecule? You can imagine lifting this one out of the page. Take it, we'll lift it up and we flop it over. Take it, flop it over. Now you can see, oh yeah, these are the same. You can always make models of these too. Like, if you make a model of this and kind of flip it over, you can see, oh yeah, now it looks like that, right? Right. So the models, your models help. Okay. All right. So we have RR. Its enantiomer is SS. What is this relationship going to be called? Diastereomer. And rather than invert both of those centers, let's just invert one now. So I'll keep the bromine steady. And the chlorine was dashed. Let's make it wedged. Now it's coming towards us. All right. Okay, so RR, this must be, RR must now be RS. You can double check that. This molecule must have an enantiomer. RS, the enantiomer must be SR, and we'll just imagine, we'll keep this oriented the same and just have the BRs go from wedge to dash. If it was RS, now it must be, the enantiomer must be SR. Okay, and what's the relationship of this molecule to this molecule? What do you think? Diastereomer, DS. What's the relationship of all the crisscrosses? They must all be diastereomers too. Okay, cool. If we wanted to draw another representation of this molecule, another representation, and the same way we did of this, we want to take, you know, to show that this can be drawn multiple ways, and they're all going to be enantiomers of this. I take this and flip it over, what does it look like? Put in parentheses maybe. Take it, flop it over. Take it, lift up, and flop it over. It'll look like a mirror image of this, because it is a mirror image of this. See now how this looks like it's a mirror image of this? Well, of course they are. They're enantiomers, right? Non-superimposable mirror images. Alright, so let's talk about miso. Let's talk about miso. We talked about miso before. Let's talk about it again. So miso molecules have 2 or more stereocenters. Stereocenters, chiral centers, alright. But they have a plane of symmetry. And by having an internal plane of symmetry, are they chiral or achiral? They're always achiral. So miso will always be achiral. Miso, if you see this miso property, it's always achiral. You will never see like miso chiral, or chiral miso or something. Sometimes I leave that as a trick answer, like just to fool you. Okay. All right. So yeah, and so meso will never be chiral. Meso will always be achiral. All right. Let's just show an example, a really quickie, simple example of meso. Okay, how many chiral centers? Well, those are 2 chiral centers. Definition of chiral center is 4 unique substituents. Those are totally chiral centers. 1, 2, 3, 4. That's a chiral center. That's a chiral center. But you have this internal plane of symmetry. So the left mirrors the right. This is a achiral meso. Meso achiral, or achiral meso, okay? Molecule. Alright, well, let's do another one. So actually, this molecule here is a meso. It's not meso. That is totally chiral, and it's a normal chiral molecule. This one has a plane of symmetry. This does not. The left does not mirror the right. So this is chiral, and if it's chiral, it has an enantiomer. And what's the enantiomer look like? I'm just going to keep the orientation the same, and just say, okay, well, Br, Br. All right. And so yeah, those are a nice pair of enantiomers, chiral molecules. But these guys are diastereomers with what? With that. Both of them are diastereomers of that. And this is a chiral or achiral? Well, this is totally meso. Okay? So, interestingly, chiral molecules can be a diastereomer with a meso molecule, right? And the meso is achiral. So this is achiral. This is achiral meso, or meso achiral. It's, yeah. Just because this is achiral meso, it's definitely not chiral. It doesn't have an enantiomer. Achiral molecules do not have enantiomers. But it can be a diastereomer of something that, you know, of, in this case, a pair of enantiomers. So that's almost always the case with meso molecules. They have diastereomers with things that are chiral and have enantiomers. Alright, so another example. Is that chiral or achiral? Or is it potentially meso? And got 2 chiral centers, but it doesn't look meso because that's not a plane of symmetry, right? You need a clear plane of symmetry through the molecule that would show it to be, you know, that would make it meso and achiral. So it is chiral. It's got an enantiomer. I'm just going to draw the enantiomer the same orientation and just say, alright, Br, Br. Those are chiral enantiomers, right? But they have a relationship with another molecule. It looks like this. And what is this a chiral molecule or not? This is a achiral meso. Achiral meso. Achiral meso molecule. Alright, because now you have the plane of symmetry right through it. So that's pretty easy to see. Just another example of that. Alright. I would say, like with cyclohexanes, like this, these are cyclohexanes, and you're used to drawing cyclohexanes as chairs. I would say don't draw in chair format here. For the purpose of seeing meso relationships and planes of symmetry, don't draw chairs. I would recommend, if you're trying to visualize this meso relationship, it's best to draw in 2D. Okay, it's just easier to see the plane of symmetry. Drawing this and seeing the plane of symmetry in a chair format is a little more tricky. Sometimes you have to go to the intermediate forms like the half chairs and the boat conformations to really see the plane of symmetry. So chair is not the best way to do it. Okay? Alright. Alright, a couple more examples. We're actually almost done with the chapter. Might be able to just finish this chapter up. What about this molecule? Is this chiral or not? This molecule, is it chiral or not? Chiral or not? We'll play the chiral or not game. Chiral or achiral, okay? So you might say, well, I see two chiral centers there, right? You do see two chiral centers. You should be suspicious of, when you have two of the same atom, like fluorine or bromine or something, you might think, oh, it might be meso. You might not see that as meso. And when I look at this, I'm like, that doesn't look, you know, I don't see a plane of symmetry here. But if I rotate the bond, and this is what I always recommend when you're trying to do these problems, rotate the bond, like rotate this bond. If you rotate that bond, and I just kind of flip it over so that I have kind of a continuous zigzag. Zigzag is now continuous, right? I rotate it. Now the fluorine on the left was wedge, it still is wedge. What does the fluorine on the right do if I flip it over? If I rotate that bond, and you can make molecules, you know, another case where your models really help. The dash 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 fluorine's going away. Flip it over, now that's where the fluorine is, right? It was away, now it is towards us. Ooh, there we go. That's meso. Meso achiral. Achiral meso, alright? What about what if I add chlorines to the middle just to make it more interesting? What if I add chlorines to the middle? Well, it doesn't really have any effect at all. We rotate it, do the same rotation. And what happens? Now, like I always recommend, when you're trying to figure out chiral or achiral, if you have something that's kind of twisted up like this, you should rotate things to align like the left side and the right side. And then you can see a potential plane of symmetry. Okay, so is this chiral or not? Is this a chiral center? Is the middle little thing a chiral center? The answer is no, that's not a chiral center. These are chiral centers. That's not a chiral center. But the plane of symmetry still goes right through it, slices right through it. Now the only kind of weird thing is, remember the chlorines are not offset to the left and right. It looks like they're offset, right? It looks like, oh, this chlorine's to the left, that's to the right. That's not true though. The chlorine is really going straight back, and this chlorine is going straight towards us. And the plane of symmetry really slices right through the back chlorine and right through the front chlorine, okay? And the left mirrors the right. It's achiral meso. Meso-achiral, okay? All right. Let me show one more. One more. All right, so this kind of looks like that, but I just wedged out the right side fluorine. Chiral or achiral? The answer is you can't see it until you align the left and right. So now I rotate the left and the right to make an extended zigzag. Left is still wedged out. What about the right now? The right fluorine was wedged. Flip it over and now it is dashed. Ooh. Is that chiral or achiral? After we rotate. That is totally chiral. Right? That is totally chiral. Absolutely chiral. And so this just shows this idea of rotating the bonds to sort of figure out if it's meso or not, right? What's the relationship of this molecule and like this top molecule up here? What's the relationship of this chiral molecule and the meso-achiral one? Relationship. Are they enantiomers? Can't be enantiomers because a chiral molecule can't, meso molecule cannot have an enantiomer because it's achiral. Achiral molecules don't have enantiomers, right? And yeah, but they're distereomers. That is a distereomer because you're flipping one stereocenter. Okay, I'm going to do two final quickie little examples. One, it's all the same, but just useful. Chiral or achiral? Chiral or achiral? Chiral or achiral? And the answer is you can't see it until you rotate the bond around to make it an extended zigzag. How many chiral centers are there? Well, that's one and that's one, right? Those are not chiral centers. That's one and that's one. All right, so you rotate, make an extended zigzag, and now we got the isopropyl on the left. Zigzag. Left methyl was wedged, it stays wedged. Right methyl was dashed, now it is wedged. Now you can see the plane of symmetry. Oh yeah, totally achiral meso. The last one. We're actually done with the chapter. Yay. Moving forward. Chiral or achiral? Chiral or achiral? The answer is you can't see it, so you rotate stuff. And I would recommend just rotating the left bond this time to make an extended zigzag. Now we have an extended zigzag. If I rotate the left, okay, right side is wedged chlorine. The left side was dashed, now it's wedged chlorine. Okay, and now this is kind of here, methyl, so it's an ethyl group, right? And this is a methyl. Okay? Now this, I just want to end with this one because it's kind of a weird one. I'll tell you it's achiral meso. It's achiral meso. And where's the plane of symmetry? Because it has to be sliced, right? So the thing is, this goes back to the idea that this carbon's going straight back, this ethyl group is coming straight towards us. The plane of symmetry slices right through the ethyl group, and you know this CH3 is all over the place. It can be straight back towards us, and this CH3 is going straight back. So we are slicing through the ethyl group and through the methyl group. Left mirrors right. Plane of symmetry is achiral meso. Okay, so this is sometimes a little hard to see and hard to visualize. I have a model of this. You can totally make a model of this. If you make a model of this, you will see it's achiral meso. Try this. This will be a little bit of work with your models. And yeah, anyway, we're done with chapter 5. On to chapter 6 next time. Alright, see ya.